Welcome to lecture 32 of our mechanics course. We are now going to start to talk about a specific interaction, specific force, and that is gravity. So far, gravity has been essentially the weight of an object somewhere near Earth. Maybe occasionally we were on Mars. Alright, it was just m times little g, the acceleration due to gravity. Well, that's going to change now, because now we want to consider gravity as a much more general theory that explains not only why stuff falls, why it falls at a constant rate, but, for example, why planets go round in circles around a star, or actually it's ellipses if you're a bit more careful about it. And you want to get a more general understanding of how gravity actually works. And of course, it's a fairly profound insight that the motion of the planets, for example, or of the moon, or of, other objects, other so-called celestial bodies, things that are up there in the sky, that the laws that govern those fundamentally are the same thing as what makes something fall on Earth. It's not at all obvious. Yet unifying those two ideas into one single explanation was the great the great insight that Newton had when he developed his theory of gravity. Now, before we go anywhere else, I want to say his theory of gravity, is true, right? But it only applies in certain regimes. So if you look at the scale of the universe, you really have to go to general relativity, which is a more advanced theory of gravity that deviates slightly from Newton on the scales of the solar system. And the examples, we can talk about those another time. And has more profound implications for how space and time work and so on. But within, say, the sort of realm of the regime of the solar system, from the size of the solar system down to the size of, small objects that you hold in your hand, Newton's theory of gravity is extremely good. Right? It's not universal. One, we don't know really how gravity works at the tiniest of scales, at atomic scales and below that, right? There are experiments going on right now that probe gravity to smaller and smaller scales. Fascinating area of research. We know that at very large scales, the size of this galaxy, solar system, Newton's theory of gravity doesn't quite hold. Size of the galaxy, we need general relativity. When we look at galaxies as a whole, there are other issues that arise there that not even general relativity by itself can explain, and we'll talk about that a little bit in the very last lecture. But right now, let's focus on this Newton's theory of gravity that, is more than sufficient to explain why this pencil falls, why the moon goes around the Earth, why the Earth goes around the sun. And we'll start by looking at what's called Kepler's laws, and these were observational laws. Johannes Kepler did observations, he gathered data, and he tried to essentially describe the motion of planets. And then we're going to put this together with Newtonian mechanics, stuff we've learned so far. And, well, where does it lead us? Well, where it leads us is Newton's theory of gravity, essentially a single expression for what a gravitational force between any two objects, well, what it looks like. And we'll look at some examples, although of course we'll explore the implication of this theory further in future videos, not in this one. Alright, so let's get started. So Kepler's laws are named after Johannes Kepler, who lived in, mostly worked in the early 17th century, early 1600s. He was instantly born about 40 minutes drive from where I grew up in southwest Germany. And by then he worked in various other places across the German states. And he had many areas of expertise, but he was most famous, at least nowadays, he's most famous as an astronomer, right? Who did observation and who gathered data and analyzed astronomical data. Interestingly, though, he actually was employed for part of his life primarily as an astrologer, right? So, fortune telling. I guess, you get a job, you do what you have to, and then you actually have insights of scientific nature in your own time. I suppose it was some kind of arrangement, but I don't actually know very much about the history here, about his personal history. Probably would be interesting to explore. But this is not about a person, this is about those laws that he formulated that describe the motion of the planets. Right? And it's crucial to understand here. He did not explain why planets move the way they move around the solar system. Right? He observed and he came up with very simple descriptive laws that told us how they moved, that summarized how they moved in a very concise way. But he didn't explain why they did that. That is what Newton's theory of gravity does. But let's look at what he came up with. And the first law is that planets move around the sun in ellipses, with the sun at one of the two foci. Okay, so here's kind of a little picture. This is my planet, this is my sun. But now chances are you've studied some Euclidean geometry, but maybe you're a bit rusty on what an ellipse actually is. Yes, you can visualize it. Oops, I want not go there quite yet. Can draw you a little sketch first. So here's an ellipse. No, here's not an ellipse. Imagine this. Let's draw an ellipse. Let's pretend we want to draw an ellipse. What is an ellipse? So here's what I can do. Imagine you stick two sticks in the ground. There's one and there's one. So we're looking down, bird's eye view. And tie a piece of string between those two sticks in the ground. Right, and the piece of string is too long. So what I can do is I can take a pen or some kind of stick to scratch the ground with, and I can make the string tight. So in this case I might pull it to here, and then here would be my pen. Right, and I can trace. I can wrap the string around my pen, and I can trace out a line. And then it might look, something like this. I might get to here. It might get to here. And what unifies all of those points is that this distance plus this distance is constant. This distance plus this distance is constant. This distance plus this distance is constant. They're all the same, because the string has a constant length, right? It's too long. It doesn't go in a straight line from here to here. It's too long, but it has a fixed length. So if I sort of trace around my pencil here, and I have a string wrapped around it, and I can trace out a line, and the line is going to look something like this. Of course, not as egg-shaped. You get the idea. It should be more uniform. And those 2 points, where my sticks are on the ground, those are my foci. So it's focus. Right? Plural of focus is foci. It's from Latin. Hope you remember your Latin declensions. Now, depending on how far those sticks are put apart, or how close they're together, and how long my string is, I can get different shapes. So for example, if they're pretty close together like this, I might compare the length of the string, I might get something that's almost circular. Actually, I've drawn it more circular perhaps than it even should have. Maybe something like this. Right, it's fairly circular. If they're exactly in the same spot, like the two foci become one, like I put the sticks right in the same spot, then I just get a circle, because the string is just going to be, twice the radius going out and back. If I put them fairly far apart, like I've done here, then I get this much longer ellipse. And this idea of how long is my ellipse versus how circular is it, it's called the eccentricity of the ellipse, but this is not a course on Euclidean geometry, so we're not going to go there. Now, but what Kepler said was, this is my ellipse, right? Planets go along a path like this, and the sun is at one of the two foci. The other one's empty. There's nothing there. Right, so let's go back to this page here. Right, so the sun's in one of the two foci, the other one's, somewhere here maybe, but there's nothing there. It was just an observation. Now, it turns out actually that the planets, at least the inner planets, are in ellipses that are almost circular. They're extremely close to being circular. You know, they're noticeably different. We can measure the difference. We don't think they're circular, but, you know, to a good approximation, you'd be forgiven if you said planets move in circles, and we're going to actually do that a bit later. That was the first law that he came up with. The second law, and I emphasize they're descriptive laws, they don't explain, they describe. It says that planets sweep out equal areas in equal time. So what does that mean? That means that as the planet travels along this ellipse, it's going to change its speed. But it changes its speed in such a way that the area it sweeps out, if you imagine having a line between the planet and the sun, is the same for equal time intervals. So imagine the planet goes from here to here, okay, from here to here, and it takes a certain amount of time. Then a planet being here to here would take the same amount of time, provided that these two areas are the same. Excuse me. So you can see that for that to be true, I would need the planet to go a lot slower when it's far away, because my slice is of this kind of skew pizza slices, right? They're longer when the planet's out here. So to get the same area here and here, it would be less wide. Being less wide means that it would have to go slower, right? It might take 3 days from here to here, but it takes 3 days from here to here. So they move faster when they're closer to the sun. But how much faster? Well, equal areas being swept out in equal times. And it actually turns out that that is a result of angular momentum conservation, and it applies to any force that's so-called central force, where something is just attracted to a point, never mind how strong that is. But that's a different story. We're not gonna go there right now. This was the second law, equal areas and equal time. And the third one is, in a sense, is the interesting one. The third one relates the period, the time once around, that's called a period, to the semi-major axis. What's the semi-major axis? Let me do another sketch for you here. So this is my ellipse. Right, it has the two foci, they might be here and here, but I can also just draw lines like this. Right, and then this long one is called the major axis. This is called the minor axis. Right. Major, it's bigger, minor is the smaller one. And then half of it is called the semi-major axis, because semi is half, and it's half of the bigger axis. Right, and the foci, the focal points, they lie on the major axis. This one would be called the minor axis, and I mean that has, you know, again, if you, on the off chance that you might have come across, or you've studied some sort of perspective drawing, and you draw circles in perspective, like a 3D perspective, the minor axis is very important because it shows you the kind of orientation of your ellipse. But it's a bit of a side note, in case, you know, it's an area that interests you. So what Kepler's saying, though, is that the semi-major axis, this length here, is proportional, or this length cubed is proportional to the period squared, or in other words, that this ratio of the period squared over that cubed, that is constant. Right, but by constant, we mean constant as you go from one planet to the next. It's constant over time, but it's also constant as you move from, you know, Mercury to Venus. Now, interestingly, this one, I mean, how did he come up with this one? I mean, this one you can sort of, you know, just look at the shape. Okay, this one is already kind of interesting. You're like, okay, well, how quickly did it move? And you find some kind of relationship, and okay, interesting discovery. But how do you come up with this is square, this is cubed? I mean, you just try all sorts of combinations? I'm not entirely sure, but let me show you the data he had. This is the data that he had. So there were 6 known planets at the time. Uranus and Neptune were not yet discovered. This was, you know, the early 17th century. But at least for those, they had a fairly good estimate for the distance from Earth, so distance from the Sun, excuse me, and the period, so the time for 1 year, as it were. So if you look at Earth first, the distance of Earth from the Sun is here given as 1, and 1 here is 1 astronomical unit, AU. AU is just literally the distance between Earth and Sun. It's kind of, we define the Earth-Sun distance, our basic unit of distance. It's often useful to do in astronomy. And so the Earth, by definition, has a distance 1 from the Sun. So the Venus is 0.724 times that distance, so it's about 72.4% of the distance from the Sun that the Earth is. And Mercury is very close, only about 0.389 times the Earth-Sun distance. Mars is about 1.5 times as far. Jupiter is more than 5 times as far, and Saturn is almost 10 times as far as the Earth is. And then for each one they had a period. Notice the Earth is just 1 year, 365.25. Of course, 0.25 is what gives us leap years. Technically it's more like 0.24 something, which is why we skip a leap year about every 100 years, except every 4th one. Don't know what I'm talking about. Look up leap years when they actually happen. It's a bit more subtle than every 4 years. But this is where this 0.25 comes in. Other planets, they have different periods around the Sun, right? Mercury takes about 3 months. Venus takes about 7 months and a bit. Earth months. Mars is not quite 2 Earth years, but getting there, and Jupiter is, 12 years, 12 Earth years thereabout. Saturn is, about 30 years, something like that. So 1 Saturn year is 30 Earth years. So Kepler had this data, and I guess he spent many a night staring at it over candlelight. I'm trying to figure out what's the relationship between those. At least that's so the story goes, and then, he had this insight and he was delighted that it's this cubed is proportional to this squared. Now, more likely, he did have enough of a mathematical understanding that he maybe plotted them on a log scale, and then you get a straight line and you can kind of read off what the relationship is. Or maybe he just systematically tried. Is this proportional to this? No. This squared to this? No. This cubed to this? No. This squared to this cubed? No, but how about the other way around? So, I doubt he was actually sitting there for years and years and years, but again, I'm not actually sure of what the exact history was. That would be a different, interesting research project. Okay, so those were the laws, and he came up with the last one, supposedly after, a long time of thinking and pondering. Now, Newton, about 100 years later, he was, of course, perfectly aware of those laws, and he tried to figure out, what's going on here. Now, he realized, look, planets, they go around, they move, and to change the direction, right, to not go in a straight line, there must be a force, and it appears that that force might always be towards the Sun. There's some kind of attraction there. And he also realized stuff on Earth gets attracted, like this pencil, it's attracted to the Earth, it falls down. So he thought, maybe those forces, they're the same thing, fundamentally. Yeah, so can we come up with some kind of force of gravity, some theory for a force of gravity that would explain both this motion as well as the fact that the pencil falls down to the ground? Now, Newton was, mathematically very capable. Among other things, he co-invented calculus. But we're not going to trace all those steps right now. That would take us too long. We'd have to explore a whole lot of background math first. Background geometry about ellipses and so on and so forth. So we're going to make a simplification. The simplification is that we'll assume that all planets actually go in circles. It's not true, but it is a pretty good approximation. And it allows us to trace the logic of Newton in a slightly simplified form. Right, so let's do that. So here are Kepler's laws for the simplified case where we assume the planets go in circles rather than in ellipses. So here is what those look like. Right, the planets go around the sun in a circle, okay, and if you take the law that the sun is at a focus to the circle, that means the sun is just at the center. Because remember, if you have both foci of an ellipse in the center, that was the picture I sort of sketched up here, they're really close together. I can imagine making the two poles in the ground, putting them in the same spot, then I get a circle, right? And the sun is just right at that point. Law 2, the planets travel at constant speed. Well, if they sweep out equal area in equal time, right? Those were our pizza slices here. Well, if this is a circle, then the only way I can have two slices of the same area is if the planet just goes round at constant speed. Right? It's a lot simpler than worrying about the area of these. If I just draw you a little picture up here, right? The planet goes from here to here. Well, if I want the planet when it's over here to have the same area, I just have to draw the same size slice. That means it's going the same distance in the same amount of time. Those two to be equal, because they're all the same length. The semi-major axis and semi-minor axis, they just become the radius in the case of a circle. So I can say period squared over radius cubed is a constant. Okay, so that is our starting point. This inside here. Okay, so let's use this to sort of retrace the logic of Newton. Now Newton, of course, he had lots of other influences. He was a philosopher, a theologier, a mathematician, right? Back in those days especially, you weren't just one special thing. You were a learned, scholarly, erudite person. And so I don't know how sort of much of a straight line it took to figure out his theory of gravity. Realistically, he probably spent a lot of time pondering, weighing the evidence, playing with ideas that didn't lead anywhere that we've never heard about. The same way nowadays people have all sorts of ideas that they think about that don't work, that never get published, and so you don't hear about them, right? But let's have this sort of simplified view of history where he just used his mind, starting with those laws, to figure out what the law of gravity might look like. So things move in circles, right? So if things move in circles, that implies that the force of gravity that's supposedly responsible must be equal to the mass of the planet times v squared over r. Right? Because they move in circles and we understand circular motion. Planets move in circles. Newton had his, theory of forces and so on, so he understood that idea. M v squared over r. The force is on the planet, right? Okay, well, we don't know about the speed, but what I do know is that the speed is, of course, equal to 2 pi r over t, right? The circumference divided by the time it takes, t here being the period. Being the circumference, distance traveled per time taken. So that then implies that I can rewrite my my force by plugging this in for v. The force of gravity is equal to the mass on the planet, the mass of the planet. So this is the force of gravity, right? I always mean on the planet. Acting on the planet times 2 pi r over t squared divided by t, right? Sorry, what am I doing? Divided by r, excuse me. Going mad already. Divide by r, there you go. So I can simplify this, and now I got 4 pi squared, squared r squared, I divide by r, and I end up with the mass of the planet times 4 pi squared times r divided by t squared, right? Because the r squared cancelled this r down here. Okay, so that's just understanding circular motion and realizing that the force that is the centripetal force that acts as the centripetal force that causes the planets to turn, not go in straight lines, that force is that mysterious force of gravity that we're trying to figure out. Okay, so now, leave this up here so you can see it. Oops. Now, I'm going to use the fact that t squared is proportional to the radius cubed. Okay, so now we're going to use t squared being proportional to the radius cubed. So that tells me that the force, this should be an implies, this implies that the force of gravity is equal, well, it's proportional, right, to the mass of the planet times 4 pi squared times r over r cubed. Notice I can't say it's equal because I'm not saying t squared equals r cubed, right? That's not what Kepler says. It's essentially t squared is r cubed times some general constant that applies to all planets the same. So that's why I have only, I know it's proportional. Now actually, now 4 pi squared is really just a constant, right? So if this is proportional to this, it's also proportional to it without that. It just changes the proportionality constant. Proportional to the mass of the planet. So then I can simplify it. R over r cubed divided by r squared. Right. So make sure it makes sense to you, right? That I can, in a way, forget about the 4 pi squared. Because being proportional just means it's equal to some constant times this. But some constant times 4 pi squared is still some constant, so it's also proportional to the same thing without the 4 pi squared explicitly included. And then I simplified the r cubed at the bottom and the r at the top to r squared at the bottom. So this is telling us the force of gravity has already two interesting properties, right? The one is, it is proportional to the mass of the thing it's acting on, and it is proportional to 1 over r squared. So if I double the distance between the objects, say the planet is twice as far out, while the force of gravity per mass is only a quarter. If I move the Earth to twice the distance it currently had from the Sun, other than everything freezing over, also gravity would be weaker by a factor of 4. Not gravity due to the Earth on us, that would be the same, but the gravity on the Earth due to the Sun. Okay, now there's still this question of, well, this is a proportionality. Well, what is this proportionality constant, or what else does it depend on, right? Because all these ones here were just for the planets. We haven't talked about anything else except planets going around the Sun. So here's what Newton must have thought at this point. He was trying to figure out more about this. So let's have a look. Newton knew Newton's laws. He probably didn't call them Newton's laws, he just called them like the laws of motion or laws of mechanics. But one thing he of course knew was Newton's third law. Right? So here's a planet, here's the Sun, and here's a planet. And so he figured out, look, there's some force of gravity on the planet due to the Sun, and we figured out that this force is proportional to the mass of the planet and proportional to the 1 over the distance squared, right? Where distance squared is just this. Now, because of Newton's third law, there is also a force the other way, and that is equal. Right? It's the same magnitude. by Newton's law number 3. So that then suggests that, look, if I apply my general law of gravity, I don't know what it is yet, I just figured out some sort of proportionality things here, like it's proportional to the mass of the object it acts on, in this case the planet. Well, I might hypothesize that it's just proportional to the mass of the object, generally, not just the planet, right? So if I ask about the gravity on the acting on the moon, well, it should be proportional to the moon. Bit of a hypothesis, but the assumption is that the laws that apply to planets apply to everything else as well. Planets are not special in that sense. So that means that the force of gravity on the sun due to the planet, that must be there by Newton's third law, that force is proportional to the mass of the thing it's acting on, and that is the sun. Right? So force of gravity would also be proportional to the mass of the sun in this case. So that means I can write the force of gravity for the sun-planet interaction as some constant times the mass of the sun times the mass of the planet divided by the distance between them, which is just the radius of the orbit. Again, because I only know proportionalities, I can't say it's equal to mass of the sun times mass of the planet divided by r squared. There's some constant here, some unknown factor still. Let's give that factor a name. Let's call it big G for gravity. And now we hypothesize that this law applies to all objects, not just the sun and the planet. Right? So this is our insight. We worked our way through it, but now we make this sort of conceptual leap of saying this law doesn't just apply to celestial bodies, it applies to everything. And, you know, that's something we'd have to test. It's not obvious. It should be so. Maybe planets and suns are special. So we hypothesize that the force of gravity for anything is equal to G times the mass of the first object times the mass of the second object divided by the distance between them squared. So here's one object, here's another object, right? And the force of gravity, it's attractive, and it is given by the mass of this one, the mass of this one, with r being the distance between them. Now from then on out, we can test this law. And it turns out to be true. At least, you know, in this kind of type of tests we can do within the solar system. At least it's true to a very good approximation. Again, we'll not talk about the slight deviations that require a more advanced theory of gravity. But this is a very good fit to the data. And it turns out this law also helps explain, for example, why this pencil falls on Earth. It relates to little g, and we'll come to that in the next video. Right now I just want to apply this. Now, the value of g is something that has to be tested experimentally, and it's not necessarily obvious how to do that. But I'll talk about that too a little bit in the future. This value of g is 6.67 times 10 to the minus 11. What are the units? Well, I want a force, newtons. This gives me a kilogram squared. I want to get rid of this. Kilogram to the minus 2, so times kilogram cancels out. I've got meter squared on the bottom, so I've got to multiply by meter squared. Cancel that out, so I'm just left with newtons. And again, experimentally established value, and the force we should add is of course attractive. Any two masses attract. So it's straight along the straight line between them. So let's do a calculation. Let's do some examples. the first thing we can do is we can just literally find the force between the Sun and the Earth as an example. For that, we need to know the mass of the Sun and the mass of the Earth. How do we know those? Different story, we can talk about that in class, and I might look a little bit about it in a future video too. Right, but just for the sake of argument, so the Sun, force of gravity between the Sun and the Earth is G, that constant, times the mass of the Sun times the mass of the Earth divided by the Earth-Sun distance, right, like this squared. At this point, you can look in the textbook, you look it up online, plug in values, so 6.67 times 10 to the minus 11. You can also nicely approximate this as 2/3 of 10 to the minus 10, if you want to do stuff in your head without a calculator. Then the mass of the Sun is 2 times 10 to the 30 kilograms. So that's a 2 with 30 zeros. The mass of the Sun. The mass of the Earth is 6 times 10 to the 24 kilograms. And the Earth-Sun distance is about 150 million kilometers, which is 1.5 times 10 to the 11 meters, and that gets squared. I'm working in meters and kilograms and newtons, of course. So now we work this out. You can use a calculator, or you can just, do it in your head, hopefully, with enough time. And here's what we get. Well, here's how we work it out, I suppose. So the way to solve this sort of thing, when you've got all these powers of 10, you don't want to get lost. Like, you don't want to make a mistake when you type this into a calculator, or even when you do it in your head. So what the trick I do is I just do this. I take all the numerical values, like the prefactors, and then I have 10 to the minus 11 plus 30 plus 24, and then I divide by this squared, so it's minus 11 and minus 11 again because it's squared on the bottom. Right? And then this, I think, comes to something like 35, I'm going to say 35.6 times 10 to the minus 11 plus 30 is plus 19, plus 24 is 43, minus 11 is 21. And, well, I guess should write this in proper scientific notation, 3.56 times 10 to the 22 newtons. A huge force, right? I'm not sure if I asked you what's the force between the Sun and the Earth, what you would guess naturally, it's probably very big. Well, this is the actual value. Let's do another quick problem, another quick example, just to round off this lecture. And that is, let's say you're sitting next to somebody at a dinner table, maybe in class, if you're allowed back in the classroom, and you're sitting next to each other. Let's make example 2. Maybe you're standing next to each other. And I ask, well, what's the gravitational force between you? Roughly. Well, let's estimate. I'm not sure what your mass is. Say one of you is 80 kilograms, maybe one of you is 60 kilograms. Distance between you, I don't know, maybe it's 1 meter. Right. So Newton's law of gravity says there's an attractive force between any two objects, so that includes human beings. Now, of course, it's a bit of an approximation because I have to assume that you both point masses, which is not true, but we just want a rough estimate so we can get away with it. How strong is that force of gravity? Well, alright, let's have a look. The force is G times mass 1 times mass 2 divided by the distance between them squared. What is this? I mean, I don't feel attracted to another person. It's not in that way, right? So is Newton wrong? Well, let's figure it out. 6.67 times 10 to the minus 11 times 80 times 60 divided by 1 squared. That's easy enough. Right, I want to get 6.67 times this 4,800, 80 times 60, times 10 to the minus 11. 1 squared is 1. Okay, it's easy enough. Let me see if I can approximate this. So 6.67 is about 2/3 of 10. So that comes to, I think, about 3,200 times 10 to the minus 10. 3.2 times 10 to the minus 7 newtons. In other words, 0.0000032 newtons. And that's why you don't feel it. Right? That is why you don't feel attracted to the person next to you, because it's the force between you two is so small. Of course, there's the obvious joke here that the heavier you are, the more attractive you are. Anyway, the next lecture we are going to figure out how does all of this relate back to the fact that if you're sitting on a planet, you're standing on a planet, why is it that I can pretend my weight is just given by m times g, not caring about this Newtonian gravity thing at all? Right, so we're going to relate back Newton's theory of gravity that we developed using Kepler's laws and analyzing planetary motion, and we hypothesized it applies to more. But how does this relate back to the gravity we know from the very beginnings of this course? I'll see you there.